Before gold is found, the Earth leaves a blueprint. Imagine standing on a lonely mountainside. No gold nuggets, no abandoned mine, no glittering quartz vein catching the sunlight. Nothing that tells you this place is different from the thousands of hills surrounding it. Yet beside you stands a professional exploration geologist. He doesn't swing a metal detector. He doesn't dig a single hole. He doesn't even pick up a rock. Instead, he quietly unfolds a large sheet of paper. Within a few minutes, he points toward one small section of the hillside and calmly says, "That's where I'd begin. How? How can someone predict where gold might exist without seeing a single nugget, without breaking a single rock, without touching the ground? It almost feels impossible. Yet this happens every single day in professional mineral exploration. The remarkable truth is, nearly every major gold discovery begins long before anyone enters the field. It begins inside a geological map. Not a road map, not a satellite image. A map that records millions of years of Earth's history. Layer by layer, fault by fault, mountain by mountain. To most people, it looks like nothing more than colored shapes and mysterious lines. To an exploration geologist, it is one of the most powerful treasure maps ever created. Not because it shows where gold is, but because it reveals where gold could never hide. That single difference has changed the way the world's greatest discoveries have been made. Today, we're stepping inside that hidden world. By the end of this documentary, you'll understand why professionals study maps for days, sometimes weeks. Before taking a single step into the wilderness, you'll discover how different geological maps work together, how they reveal Earth's hidden architecture, and how they quietly guide geologists toward some of the richest gold deposits on the planet. Before we begin, I'd love to know something. What time is it where you're watching this documentary? And which country are you joining us from today? Leave your answer below. It's always fascinating to see where fellow explorers are watching from around the world. Now, let's unfold the first map. Because every remarkable gold discovery begins with understanding the ground beneath your feet. The Bedrock Geological Map. Reading Earth's original foundation long before rivers carved valleys. Before forests covered mountains. Before humans gave names to continents. The rocks beneath our feet were already writing Earth's history. A Bedrock Geological Map is simply a map of that history. Instead of showing roads, cities, or rivers, it shows something far more important. The actual rock formations hidden beneath the soil and vegetation. Think of it as removing every tree, every building, every layer of loose sediment, until only the original foundation of the Earth remains. That is exactly what a Bedrock Geological Map attempts to reveal at first glance. The map appears confusing. Bright colors cover the landscape. Thin black lines divide one area from another. Letters and symbols seem almost impossible to understand. But none of them are random. Every color represents a different rock unit. Every boundary marks a change in geological history. Every symbol tells part of a story that may be hundreds of millions, or even billions, of years old. For an exploration geologist, those colors immediately answer an important question. What kind of rocks am I actually standing on? Because gold doesn't occur equally in every rock. Some rocks have almost no relationship with gold. Others have hosted some of the richest deposits ever discovered. Understanding that difference allows professionals to eliminate enormous areas before they even leave the office. Imagine two neighboring hills. They look almost identical, both covered with shrubs, both scattered with weathered stones, both crossed by small streams. To most people, there is no reason to choose one over the other, but a Bedrock Geological Map quietly reveals something invisible. One hill is underlain by young sandstone. The other rests upon ancient metamorphic rocks, cut by quartz veins and intrusive granites. Suddenly, those two ordinary hills are no longer equal. One has a geological history far more favorable for gold mineralization. The map hasn't found gold. It has simply identified the better question. Now the investigation truly begins. Among the first rock types geologists look for are greenstone belts. These ancient volcanic and sedimentary rocks are among the world's most productive gold hosts. Many of the great gold camps of Canada, Australia, and parts of Africa owe their existence to these incredibly old geological terrains. Then come schists and slates. These metamorphic rocks often develop under immense pressure, creating fractures and pathways through which hot, mineral-rich fluids once circulated. Those fluids are responsible for transporting and depositing gold deep underground. Another important feature is granitic intrusions. Not every granite contains gold, but many gold systems formed as hot fluids migrated around cooling granitic bodies, creating favorable conditions nearby. The map begins revealing relationships that are impossible to recognize from the surface alone. Then there are quartzites, volcanic formations, altered sedimentary rocks, and intrusive diorites. Each contributes another piece to the geological puzzle. Individually, none guarantee a discovery. Together, they begin narrowing thousands of square kilometers into a handful of highly promising targets. But a map alone is never enough. This is where geology leaves the paper and enters the real world. A geologist arrives at the hillside the map predicted. Now the colors on the paper must match the rocks beneath their boots. Does the mapped granite actually appear at the surface? Are the schists weathering exactly where expected? Is the quartzite exposed where the contact line was drawn? Every observation either strengthens confidence or raises new questions. The map becomes a conversation between science and nature. Sometimes the landscape confirms everything. Sometimes it reveals surprises the map couldn't show. And that is exactly why a geological mapping and field observation always work together. One without the other tells only half the story. Yet even the best bedrock map cannot answer the question that matters most. It can tell us what rocks are present, but it cannot explain how gold-bearing fluids move through them. For that, geologists turn to another map, one that reveals Earth's hidden fractures. The pathways through which gold itself began its journey millions of years ago. The Bedrock geological map answers the first question: what rocks are here? But another mystery remains. If gold formed deep beneath the Earth, how did it ever reach these rocks in the first place? The answer isn't written in the rocks themselves. It's written in their fractures. Imagine holding a perfectly solid piece of granite. No cracks, no openings. Now imagine trying to force hot, mineral-rich fluids through it. Almost impossible. But wait a few million years. Powerful tectonic forces begin pushing continents together. Mountains rise, pressure builds, the Earth's crust bends, breaks, and suddenly, tiny fractures begin spreading through the rock. Some remain only a few centimeters long, others stretch for hundreds of kilometers beneath the surface. These fractures become the Earth's hidden plumbing system, and this is exactly what a structural geological map is designed to reveal. Unlike a bedrock map, a structural map doesn't focus on rock types. Instead, it shows the architecture of the Earth's crust. Faults, shear zones, folds, fracture systems, contacts. Each one tells a different story about how the landscape has been deformed over millions of years. To most people, they're simply lines crossing a map. To an exploration geologist, they are possible highways that once carried gold-bearing fluids. One of the first features professionals search for is a major fault. Faults are fractures where enormous blocks of rock have moved relative to one another. Some moved only a few meters, others shifted entire mountain ranges. During these movements, the crust briefly opens. Pressure changes. Hot fluids deep underground begin rising through these newly created pathways. As those fluids cool, quartz begins crystallizing. Sometimes, gold crystallizes with it. This is why so many productive gold deposits are found close to ancient fault systems. Not because faults create gold, but because they provide the routes that allow gold-bearing fluids to travel. Yet one fault alone rarely tells the whole story. Experienced geologists become especially interested when two or more faults intersect. These intersections often create zones where fluids slow down, pressure drops, and minerals begin depositing more efficiently. Think of it like traffic entering a busy intersection. Movement changes, space opens, everything begins collecting in one place. Nature often behaves in surprisingly similar ways. Then there are shear zones. At first glance, they may resemble ordinary faults, but instead of breaking suddenly, the rocks have been slowly stretched, squeezed, and deformed over immense periods of time. This constant movement creates thousands of tiny fractures. Each one becomes another possible pathway for mineral-rich fluids. Some of the world's richest lode gold deposits were discovered within ancient shear zones, not because the rocks looked impressive, but because the structural map revealed what could never be seen from the surface. Another feature quietly catches a geologist's attention: fold structures. Layers of rock that were once flat have been bent into enormous arches and troughs by tectonic forces. Where these folds tighten, new fractures often develop. Those fractures may later fill with quartz, sulfides, and occasionally gold. The folds themselves are not the target. They simply help identify where the Earth became weak enough for mineralizing fluids to enter. Then comes one of the most overlooked relationships in exploration. A bedrock map may show favorable host rocks. A structural map may show a major fault. Neither alone guarantees anything. But when a fault cuts directly through favorable host rocks, the investigation suddenly becomes much more interesting. This is where professional geologists begin stacking evidence, not assumptions, evidence. One map supports another. One clue strengthens the next. The search area becomes smaller, and the confidence becomes greater. Eventually, the geologist leaves the office. The map is folded away. Now the hillside must answer a simple question. Did the Earth's structure leave visible fingerprints? Broken quartz veins, sheared rocks, offset layers, polished fault surfaces, iron-stained fractures. These aren't random observations. They are field confirmations. The landscape is either agreeing with the structural map or quietly correcting it. Every outcrop becomes another conversation between the map and the mountain itself. Sometimes, one exposed fracture completely changes the understanding of an entire district. Sometimes, one missing structure sends geologists back to redraw their interpretation. That is the remarkable thing about geology. Maps are never guesses. They are scientific interpretations, constantly tested against reality. Yet even after understanding the rocks and the structures that carried mineral-rich fluids, a geologist still faces another challenge. The gold itself may remain completely invisible. No quartz vein at the surface, no exposed mineralization, nothing to catch the eye. So how do professionals continue narrowing the search? The answer lies in chemistry, because long before gold becomes visible, the surrounding elements often begin revealing its presence. Imagine searching thousands of square kilometers without seeing a single piece of gold. No nuggets, no quartz veins, no abandoned mines. Nothing. Does the investigation stop? Not even close. Because professional geologists understand one remarkable truth. Gold is one of the most difficult metals to detect directly. It often exists in extremely small concentrations, sometimes completely invisible to the naked eye. So instead of chasing gold itself, they begin chasing the elements that quietly travel with it. This is where geochemical maps become one of the most powerful exploration tools ever developed. Unlike bedrock maps or structural maps, a geochemical map doesn't tell us what rocks are present. It tells us what those rocks contain. Every color, every contour, every small anomaly represents the chemistry of the Earth itself. But where does that chemistry come from? The answer begins with sampling. Professional geologists collect hundreds, sometimes thousands, of samples across an exploration area, not randomly. Every location is carefully planned. Some samples come from soil. Others are collected from stream sediments, fresh rock chips, even fine sediments trapped along seasonal drainage channels. Every sample is carefully labeled, recorded, and sent to a laboratory. There, Highly sensitive instruments measure the concentration of dozens of chemical elements, sometimes even parts per billion, far beyond anything human eyes could ever detect. Then, those results are transformed into a geochemical map. At first, the map appears simple. Different colors spread across the landscape, but every color is telling a chemical story. One area contains unusually high arsenic. Another shows elevated antimony. Farther away, copper quietly increases. Individually, these elements may seem unrelated. Together, they often point towards something much more valuable. Because gold rarely travels alone. As hot hydrothermal fluids moved upward through ancient fractures, they carried entire families of dissolved elements. Gold was only one passenger. The surrounding elements left their own fingerprints throughout the system. These are known as Pathfinder elements. One of the most important is arsenic. To most people, arsenic sounds dangerous. To exploration geologists, it can be extremely useful. Many significant gold deposits around the world are closely associated with arsenic-bearing minerals. When arsenic concentrations suddenly increase, the investigation becomes much more interesting. Another important companion is antimony. Although rarely valuable by itself in small concentrations, its presence often suggests that the same hydrothermal fluids responsible for transporting gold once moved through the area. Then comes bismuth, less common, but highly significant in certain gold systems. Finding elevated bismuth doesn't guarantee gold, but it strengthens the geological story already being built. The same applies to tungsten in some mineral districts. Tungsten quietly accompanies gold mineralization. It becomes another piece of evidence, not proof, evidence. Other Pathfinder elements include silver, copper, lead, zinc. Each behaves differently. Each responds to changing temperatures, pressures, and fluid chemistry deep underground. Professional geologists rarely focus on just one. Instead, they study how several anomalies overlap. That overlap is where confidence begins to grow. Imagine one hillside. The structural map reveals a major fault. The bedrock map shows favorable host rocks. Now the geochemical map displays elevated arsenic, antimony, and traces of gold. Three completely different data sets, quietly pointing toward the same location. This is no longer coincidence. It is a geological conversation. Every independent piece of evidence is beginning to agree, but chemistry isn't limited to laboratory. Sometimes, the landscape reveals chemical change with your own eyes. Rust-colored rocks, yellow-orange staining, soft altered zones, bleached outcrops. These visible changes often result from hydrothermal alteration. Long after the mineralizing fluids disappeared, the rocks continued recording their passage. Nature left permanent signatures across the hillside. Some exploration teams discover these alteration zones before finding a single quartz vein. Others recognize them only after comparing field observations with laboratory results. Either way, the chemistry quietly guides the investigation forward. Yet chemistry alone still cannot answer one critical question. The elements may suggest that a mineral system exists, but they cannot reveal what remains hidden hundreds of meters beneath the surface. For that, geologists must begin seeing through solid rock itself, without drilling, without excavation, without removing a single layer of soil. And remarkably, modern exploration has found a way to do exactly that. By now, the investigation has already uncovered an extraordinary amount of information. The bedrock map revealed the foundation. The structural map exposed the hidden pathways. The geochemical map identified the chemical fingerprints. But one mystery refuses to disappear. What is actually hidden beneath the ground? Standing on a quiet hillside, everything still looks ordinary. Grass, weathered rocks, a few scattered shrubs. Nothing suggests that hundreds of meters below your feet, an entire mineral system could be waiting. This is where exploration enters one of its most fascinating stages, not by digging, but by listening. Professional geologists call this geophysical exploration. Unlike geological maps, geophysical maps don't identify rock types directly. Instead, they measure the physical properties of the Earth, tiny variations, completely invisible to human eyes, become visible through science. One of the oldest and most widely used methods is the magnetic survey. Every rock contains tiny amounts of magnetic minerals. Some contain almost none. Others produce remarkably strong magnetic responses. By measuring these subtle differences, geologists can begin outlining buried rock formations, ancient volcanic belts, intrusions, and major fault systems. The map doesn't show gold. It shows the geological architecture where gold may have formed. Sometimes, a magnetic anomaly becomes the first indication that something unusual exists beneath the surface. Then comes the gravity survey. It sounds almost unbelievable. Yet geologists can detect differences in the Earth's gravity caused by rocks hidden hundreds of meters underground. Dense rocks produce slightly stronger gravitational attraction. Lighter rocks produce less. The difference is incredibly small, but modern instruments can measure it with astonishing precision. Those tiny variations help reveal buried intrusions, deep basins, and structures that never appear at the surface. Another powerful tool is the electromagnetic survey, often called an EM survey. Instead of measuring gravity, it measures how easily rocks conduct electricity. Some rocks resist electrical currents. Others, especially those containing sulfide minerals, conduct electricity much more efficiently. Many gold deposits occur alongside sulfide minerals such as pyrite, arsenopyrite, or chalcopyrite. Finding conductive zones doesn't prove gold exists, but it highlights places worthy of closer investigation. Then comes one of exploration's most remarkable techniques, induced polarization, usually shortened to IIP. At first, the name sounds highly technical. The principle is surprisingly elegant. A small electrical current is introduced into the ground. When the current is switched off, certain minerals briefly continue holding an electrical charge before slowly releasing it, almost like tiny underground batteries. Sulfide minerals respond particularly well. That delayed response becomes another valuable clue. Around the world, many major gold discoveries have begun with strong IP anomalies. Not because IP detects gold directly, but because it detects the mineral systems often associated with it. Another fascinating method quietly works from above. Radiometric surveys. These measure the natural radiation emitted by elements such as potassium, thorium, and uranium. Gold itself produces almost no useful radiometric signal, yet changes in surrounding rock chemistry often alter these natural radioactive patterns. Geologists compare those variations with geological mapping, searching for alteration zones that may indicate ancient hydrothermal activity. One dataset supports another. Piece by piece, the underground picture becomes clearer. Yet even with all these remarkable technologies, professional geologists rarely trust one map alone. A magnetic anomaly, combined with a favorable structural corridor, supported by geochemical anomalies within the correct bedrock, suddenly becomes far more convincing. Exploration is not about chasing one exciting result. It is about building confidence, one independent line of evidence at a time. But perhaps the most extraordinary tool of all never enters the ground. It never measures gravity, never sends electricity into the Earth. Instead, it quietly watches the planet from hundreds of kilometers above. Satellites, every single day. They record landscapes in astonishing detail. Not simply photographs, but information beyond ordinary human vision. Subtle changes in vegetation, iron-rich alteration, clay minerals, ancient drainage patterns, hidden lineaments stretching across entire mountain ranges. Features that may never be recognized while standing on the ground suddenly become obvious from space. Imagine that. A hillside that appears completely ordinary from a few meters away can reveal an entirely different story when viewed from orbit. By now, the investigation has reached an extraordinary point. The rocks, the structures, the chemistry, the hidden physics, and even satellites are all beginning to tell the same story. Yet one final challenge remains. Maps can predict, science can measure, technology can reveal, but sooner or later, every exploration program arrives at exactly the same place. The geologist closes the maps, puts away the instruments, walks back onto the hillside, and asks one final question. Does the Earth itself agree with everything we've learned? Because in the end, the greatest geological map is still the landscape beneath your boots after hours, sometimes weeks, of studying geological maps. The investigation reaches its most important moment, not inside a laboratory, not in front of a computer, but back where every discovery truly begins. On the ground, the maps have already spoken. Now, the Earth must answer. Imagine arriving at a hillside you've never visited before. To everyone else, it looks completely ordinary. Scattered rocks, dry grass, a few exposed outcrops. Nothing immediately suggests that this place deserves attention. But this time, you are no longer seeing the hillside with ordinary eyes. You begin remembering the maps. The Bedrock geological map told you the hillside is underlain by ancient metamorphic rocks intruded by granite. The structural map revealed a major shear zone crossing the slope. The geochemical map highlighted elevated arsenic and antimony nearby. The magnetic survey outlined a buried structure extending beneath the ridge. The induced polarization survey suggested sulfide mineralization at depth. Satellite imagery identified iron-rich alteration following the same structural trend. 6 completely different investigations, 6 completely independent datasets, quietly pointing toward the same hillside. That is not coincidence. That is confidence. Professional exploration is never based on one exciting result. It is based on agreement. Every map must support the next. Every observation must strengthen the previous one. Only then does the search truly begin. As you climb the slope, the first field confirmation appears, broken quartz fragments, exactly where the Bedrock map predicted. A few steps farther, the rocks become heavily fractured, just as the structural interpretation suggested. Then, rust-colored staining begins appearing along the outcrop. Hydrothermal alteration, exactly where the geochemical anomalies become stronger. Nothing here is dramatic. No giant gold nugget waiting on the surface. No glittering vein stretching across the hillside. Instead, nature quietly confirms each prediction, one clue after another. This is why professional exploration rarely depends on luck. By the time geologists collect their first field sample, they already understand the geological story surrounding it. Even then, the investigation continues carefully. Rock samples are collected from fresh outcrops. Soil samples are taken along carefully planned grid lines. Small stream sediments are gathered downstream to compare with laboratory results. Every sample either strengthens the geological model or forces it to change. Good geologists never become attached to assumptions. They follow evidence. Sometimes the evidence confirms everything. Sometimes it leads in an entirely different direction. Both outcomes are equally valuable. Because exploration is not about proving yourself right. It is about discovering what the Earth is actually saying. Eventually, only after the maps, the chemistry, the structures, the field observations, and the samples all begin agreeing. Does drilling become an option? That surprises many people. Most believe drilling comes first. In reality, it often comes last. A drill hole is one of the most expensive decisions in mineral exploration. Every meter drilled should answer a geological question that the maps have already prepared. And when a drill finally intersects a gold-bearing quartz vein, the discovery rarely feels like luck. It feels like the final sentence of a story that began long before anyone arrived. That is the remarkable power of geological mapping. It doesn't reveal treasure directly. It reveals understanding, and understanding quietly leads explorers toward discovery. The next time you look at a geological map, don't see colors, see continents colliding, see volcanoes cooling beneath ancient oceans, see mountains rising, breaking apart, and slowly releasing the minerals that rivers would one day carry. Every symbol, every line, every shaded polygon represents millions of years of Earth's history compressed onto a single sheet of paper. Professional geologists don't see maps as drawings. They see conversations with the planet itself, a conversation that began billions of years ago and continues every time someone unfolds another geological map. Perhaps the greatest lesson isn't how to find gold. It's understanding that gold is only one chapter in a much larger geological story. Long before a prospector swings a detector, long before a nugget catches the sunlight, the Earth has already written the answer. Patiently, fault by fault, rock by rock, layer by layer. The map simply teaches us how to read it. And perhaps that is the greatest discovery of all, because somewhere, right now, a geologist is quietly unfolding another map, looking at another hillside, following another pattern invisible to everyone else. The next great discovery may not begin with a shovel, or a metal detector, or even a gold nugget. It may begin with a single line drawn across a geological map. Thank you for joining this exploration into one of the most powerful tools in modern mineral discovery. If this documentary changed the way you see geological maps, tell me in the comments. Which type of geological map surprised you the most? And what technical exploration topic would you like EGSPRO to uncover next? Until our next expedition, keep exploring, keep questioning, and remember, the greatest gold discoveries are often made long before anyone touches the ground.